I wish you had my imagination.
All right, today let's look at how to do conjugate heat transfer inside LSdyna. The agenda for today is I'm gonna go over the basics. Essentially looking at some of the theory and the governing equation related to conduction, convection, how the interface is handled between fluid and solid side inside LSdyna. We can look at some of the general mechanisms for CHT in Dyna. Look at the relationship between the different between the velocity boundary layer and the thermal boundary layer to make sure we're making good decision when it comes to meshing with respect to the CHT problems. And we're gonna look at strongly coupled, weakly coupled CHT problems. All right, and then we're gonna dive into a little bit more detail into specific keywords and keyword templates. I'll go over the general framework for how I will actually set up a problem like this. These problems, they are so useful, so generically useful in most cases, which is why I think it's worth doing. I'm actually gonna, in the future, I'm gonna do 4 more videos, which I will explain a little bit at the end. Basically, I'm gonna make this a 5-part series related to CHT and Dyna. We're gonna target theory. We're gonna target basic principle behind the model setup. We're gonna look at key deals related to a template that can be applied to many different type of similar CHD application in the world. Okay, all right, let's get started. All right, so when we talk about doing a problem between fluids and structures, right? You can do a fluid structural interaction, which is about transmitting or exchanging information related to the displacement and the force between the two sides, right? But when we talk about conjugate heat transfer, what we're doing here is actually this transfer information related to heat flux through an interface between the solid and the fluid, right? Solids are mostly conducting heat, whereas fluid are mostly transporting heat through convection, natural convection, forced convections. But the way when they interact with each other, right, there's also a heat exchange at the interface, which is the key to try to capture with a CST problem. Okay, and that's essentially what we're gonna be looking at today. All right, the basic heat equation that's being solved in Dyna or in most other solver out there, right? We're essentially solving for the relationship between the conduction and the convection inside the system, right? So I broke down the original equation from an Einstein notation to essentially the notation that's most commonly seen. But basically over here is your convection term, right? That's essentially the change of temperature due to fluid motions. And then you have your conduction term, right, which is your thermal diffusivity, right? Your thermal diffusivity, which is your alpha here, right? And it's also with second order derivative with respect to space. We usually can have a heat source that can be applied to the system, and of course you also have some kind of transient effect, right? The governing equation help us frame the problem, right? We're essentially solving the fluid side, we're solving the solid side. We need to consider a heat source, and we need to consider any type of transient effect in a CHT problems. The coupling between the two, obviously, right, is that they have to maintain a thermal equilibrium, which is why this equation makes sense. Now, if we look at the conduction side, right, it's Newton law of cooling. Basically, I'm sorry, it's the thermal conduction, right? Basically, you're basically generating heat flux due to a thermal conductivity and a delta T from the systems, right? The thermal conductivity is obviously a material characteristic, which we're going to be looking at. On the convection side, obviously, depending on the velocity, the fluid velocity, right? The heat transfer coefficient H is usually the thing that we'll look at, right? So natural convection, you have something that's much lower. For forced convection, where depending on the nature of the gas, you can have a much higher fluid velocity, and therefore you're gonna have essentially forced convection, where the heat transfer is due to the motion of the fluid taking heat away from the surface. And that's the basic principle of convection. And then depending on the nature of the fluid itself, right? We can have natural convection, forced convection at specific velocities. and then usually you want to calculate a H value that you can directly use in a structure-only thermal analysis, for example. All right, so when we want to think about, is it a natural convection dominant problem or a forced convection dominant problem, right? What we can do is use the Richardson's number. The Richardson's number is basically the ratio of your buoyancy force to the inertial force of your fluids, right? This ratio tells us, are we mostly looking at natural convection or are looking at forced convections? Of course, the buoyancy force, right, is if it dominates, then you essentially have natural convection because natural convection is due to buoyancies, right? If you don't have, if it's a very low number, then you essentially have your inertial force dominate, and that's due to the velocity of your fluids, and that's gonna essentially be due to forced convections. It seems intuitive, right? That's why the way the Richardson number is defined is essentially based on this. What's useful about this is that you can gut check the nature of your problem. Basically, you can calculate based on how fast the fluid is moving, right? You can also look at your delta T and look at your length scale, and that together tells you, are you looking at a problem that's mostly natural convection or are you looking at forced convections, which is why this number is useful. Also, we can look at the Rayleigh number. Rayleigh number essentially tells us the nature of the natural convections, right? Is it in a laminar region, or is it either in turbulent region, or is it in transitions? Richardson's number is essentially your buoyancy of the problem against the viscous resistance. So in a lot of ways, if you have a natural convection, you can also look at the nature of the fluid flow due to natural convection, due to that buoyancy effect, and then is it going to be in the laminar region or the turbulent region? So to help you characterize the nature of the fluid using the Rayleigh number. The Nusselt's number basically tells you if you are looking at a problem that's mostly convection dominated or conduction dominated, right? HL over K is a very quick way in which you can check the nature of your problem, looking at essentially based on the heat transfer coefficient, you can sort of tell is it going to be a convection dominant problem or a conduction dominant problem, and that allow you to simplify the nature of the problem. So when you're looking at doing a CHT analysis, right, you don't always have to model the fluid side, right? That's the kind of thing that we want to think about when we start to set up a problem, right? So what I've done when I look at these dimensionless number inside CFD, right, I always think that it's pretty difficult to try to remember what they are, right? But what's much more important, in my opinion, right, is have a summary of what they are inside like a table, exactly like this, right? And come back and look at them when you set up a problem, right? It's often a very good first order gut check against what you're looking at, and that's really helps you with essentially a good strategy for setting up a CHD problem, is that you have to look at the fluid side and understand the nature of what you're actually looking at, right? It's easier for me as a structural guy to visualize the nature of my problem on the structure side, but on the fluid side, it's going to be a lot more difficult for me, which is why I took the time to build the table. These table basically give me a very good understanding of what kind of problem I'm trying to solve on the CFD side. Okay. All right, so I'm not going to go over every one of these, right? The ones that I laid out, these are mostly related to heat transfer, right? Which is what I wrote down here. Okay. Of course, when we talk about CHD, the most important step, and that's the step that you're not just doing a fluid side, you're not just doing a solid side, you're trying to look at the relationship between the two, right? Is that we actually have to define an interface. So heat transfer from the fluid side to the solid side, right? That's usually where you define that interface. This interface has two different options currently in Dyna that you can actually look at. One is essentially by looking at a constraint option, right? In this case, I think the biggest requirement is that the fluid side nodes need to be usually be finer than the solid side, because you're essentially mapping the fluid side to the solid side. You don't actually you don't actually have any temperature loss between that interface. That allows you to basically look at what happens. You can also use a mortar contact, which is essentially like a thermal contact that you can do with a structural thermal problem. A structural thermal problem, you use contact to define interface, right? A fluid thermal problem, you can also use contact to define an interface. But I think the constraint method is probably going to be a more standard one, right? So over here is an illustration I found from a paper related to a constraint method. Basically, you're essentially defining the constraint equation between the two sides, right? On the contact side, you actually have an interface that you are essentially defining based on the mortar contact that you're defining here. I'm likely not going to use this unless I have a very good reason. The mortar contact allow you to have a higher mismatch between the fluid nodes and the solid nodes. Alright, so if that mismatch is something I have to have, then maybe I will use a mortar contact, but otherwise I will use a constraint layer contact, which means I want to make sure my nodes mostly match up, and it's usually a good habit for me to get into as well. Okay, so if we look at the thermal boundary layer, right? So in fluids, right, we have the velocity boundary layer, right? Which means we'll have to try to resolve the velocity profile near the wall, which essentially is a very sharp gradient that you have to essentially resolve, right? Usually you want to get to like a y plus of 1, right, to have a perfectly resolved boundary layer. In the thermal side, you have something essentially very, very similar, right? It's not the same as velocity profile, but it is a very similar thing we'll have to look at. There's a very sharp gradient for the heat transfer, for the thermal gradient across near the boundary as well, because of the nature of heat transfer between fluid and solids. Okay, well, so one thing that I read, right, is a good thing I wrote down is that the velocity boundary layer does not care about the temperature boundary layer, but the temperature boundary layer is heavily dependent on the velocity boundary layer, which obviously makes sense because the faster the fluid goes, the more the heat transfer is going to be affected by it, right, which essentially is the case that we're going to be looking at. So one of the questions I had obviously is that how do you properly define the velocity boundary layer? Because, I'm sorry, how do you properly define the thermal boundary layer? Because it's not the same thing. You can't just look at the y plus and know that you're doing the right thing, right? And then the solution to that is that you have to look at the Prandtl number. I'm hoping I said that correctly, right? The Prandtl number right here is essentially the thing that you are looking at to really define the velocity boundary layer. I'm sorry, to define the thermal boundary layer. So for gases, so I wrote down some quick notes here. For gases, it's going to be around 1, right? Which means your velocity and the thermal boundary layer are approximately the same. For liquids, PR is going to be way higher, and then for like a very viscous material, you're going to have something that's very, very small. So how does Prandtl number play into the boundary layer, the thermal boundary layer calculations, right? It's actually calculated based on this number here. Basically, the thermal boundary layer and the velocity boundary layer is going to have a relationship that's with respect to the Prandtl number, right, to the order of like -1.3, and the Prandtl number is obviously your momentum diffusion versus your thermal diffusions. This is something that you can essentially look at, right? So given the nature of the fluid, for example, if it's air, you're going to have a thermal boundary layer that's going to be slightly higher than the velocity boundary layer, which means you're usually good if you keep them the same. For water, you're going to have a thermal boundary layer that's going to be a little bit smaller than the velocity boundary, which is about half of it. Right, so if you're looking at a viscosity of, if you're looking at a fluid that's around air, you can use like approximately the same thickness. If you use water, you have to make sure you have a much smaller thermal boundary layer, which is usually a good rule of thumb to have for this kind of problems. All right, so of course, if you don't want to fully resolve the velocity boundary layer, because it might require a mesh that's really fine, right? What we can do is use the law of wall, right, which is the thing that you have on both the velocity side as well as the thermal side. In LSdyna, thermal wall function can be defined in the same location as your turbulence model, right? Basically, if you don't activate the law of the wall, this is basically how you calculate the heat transfer across the thermal boundary layer, and what is your first layer thickness. If you do activate it, I actually copied this from the documentation from one of the paper, which I thought gave a really good explanation about what's happening, right? So you can actually sort of calculate what is your thermal boundary layer needs to be, right? And then how the wall is actually activated based on that. Basically, the turbulent heat flux will actually be calculated as an additional variable, which is the thing that we're essentially looking at here. And for me, I think it's going to take a little bit of experimentation as I work on the example problems, right? And if you can make the mesh dense enough, you're going to get a better results. And then you can use this here as a guideline. I'm going to use this as a guideline to sort of know how to properly calculate the appropriate when to decide to turn on the thermal law of wall, right? Law of the wall, and also how to calculate the proper thermal boundary layer for that kind of problem. Like I can check my y plus to make sure it's within, like, say, I think it's like the 30 to 300 or something like that, right? If I check correctly, yeah, it's a 30 to 100. If I use a wall function, right, I can essentially ensure my y plus is appropriately defined, right? And this is something that we can essentially do. Basically, you can look at your y plus and make sure it's within the range of your wall functions, right? Of your law of the wall, and then you can activate the law of the wall to have the proper thermal heat transfer across the boundary, across the interface. You can also use a full turbulence model and just make sure y plus is very, very small, around 1, if you can get away with that. From what I've done, I feel like often it's very difficult to get y plus to be exactly around 1. Often you have to make your mesh really, really fun to get there, and that make the model very, very expensive, especially if you want a smooth transition between the finer region and the coarser region of the model. So depending on where you're working on, it could be very, very expensive to implement, which is why I think the wall function could be something that we can look at as a way to properly resolve the heat transfer across the interface. All right, so in addition to that, right, we can activate a strongly coupled or a weakly coupled. This is a coupling option. I'll change the title. Right. The coupling option, obviously, just like FSI, have weakly and strongly coupled FSI, weakly coupled FSI. Inside a CHT analysis, you also have a weakly and strongly coupled methodologies, right? So if you set this parameter here to 0, you have a strongly coupled one. Otherwise, you have a weakly coupled one. The basic difference, I think, is just a compute speed. And also, can you decouple the thermal problem and the mechanical problem from each other so they don't solve at the same DT, right? Because the fluid side usually have to solve a much lower DT than, say, for example, the solid side, especially, or the thermal side. The thermal side is going to, I think, require the least amount of DT, right, to solve. So you don't actually have to have all two sides or all three sides solve at the smallest DT. And it usually helps. Obviously, the downside is that you have some loss in terms of the heat transfer accuracy, because you basically have to solve a lot of steps on the fluid side before you transfer the data to the solid side. For heat transfer or for FSI, if you do FSI analysis, it's the same idea, right? The interface becomes slightly different. So this is where you can look at the nature of the problem to see if you can get away with a strongly coupled problem. If not, then you just do a weakly coupled problem. Just be aware of the DT difference and set up the problem correctly, right? I think from experience, I know I want to look at the DT requirement for my structure side, for my fluid side, for my thermal side independently to make sure I'm capturing the right DT number, right? And then decide if I want to do a strongly coupled problem and how long it would take. I can actually test that out. I'm going to show you in a second my template. My template is going to give a very good idea about how to actually think about the nature of setting up a more complex multiphysics problem, right? Because this DT difference is the thing that we have to pay attention to. Okay, so let's look at a couple main keywords for CHT that we haven't looked at before, right? The first thing is the ICFD boundary conjugate heat, right? This is the one in which we can define the nature of the interface, right? Is it constraint versus mortar? Usually it's going to go with constraint, right? And then you can also define some type of a temperature drop across interface. If you have any reason to believe there's a reason for a temperature drop between the interface, you can also define that there. Pretty simple. We can also look at the database HTC. This is what allows us to actually generate a heat transfer coefficient value as a database output. Obviously, the H value is going to be calculated based on your velocity of your profile and your DT across the interface, and that's essentially the number that you can use in a separate analysis, right? The H value that you often have to use for convection boundary conditions is something that usually is a result of the CFD analysis, and this is where you can actually output the H value. We can also look at the FSI interface. So interesting enough, for a conjugate heat transfer, the FSI control card also needs to be included, right? And that's what tells the problem that you're doing a coupling analysis. So interestingly, that's also something we will have to do to include. So this is a copy paste from my previous ICFD control FSI keyword that we can also look at here. Okay. Obviously, when we talk about weakly versus strongly coupled CHT problem, you can set the C type to 1 or 0. 0 means it's a strongly coupled, 1 means it's weakly coupled. And once you turn on both, you can sort of see one of them is actually going to give you a node saying the monolithic thermal couple, that's a strongly coupled, or you have a weak thermal couple, that's a weakly coupled, right? And if you look at the difference in the log file, you can barely tell the difference. Basically, if the DT is different between the CFD side and the mechanical side and the thermal side, you will solve a bunch of ICFD time step before you solve the thermal time step, right? That effectively makes it a weakly coupled problem. But in a sense, right? In a sense, but what's really happening is that you are essentially solving the data transfer between the two every so often as you're doing. And if you're using a weakly couple, you're essentially pass it as a Dirichlet boundary condition, right? Otherwise, you do a strongly coupled monolithic solve, you're basically transferring data back and forth all the time, which is just more expensive. I think this one is like 20% more expensive than this one based on a very simple model that I was able to test, right? Basically be aware of that. I think in reality, it's really just the compute time is the biggest difference between these two. Of course, accuracy that you gain from the actual compute time over here as well. Okay, so let's look at the overall governing workflow for a thermal fluid CHD problem. In a lot of ways, if you can do fluid structural interaction, you can do conjugate heat transfer. You can also do a thermal structure analysis, because these three are really just tied together. Like I have video about the thermal structure, I have video about the structure fluid, and now I have video about the thermal fluids, right? In addition, the beautiful thing about Dyna is that you can actually solve all three equations very easily together in a Dyna setup, right? People say Dyna is difficult, but this is where it truly shines, because I can show you how easy it is to set up a problem that has three different type of solvers involved, right? You have the thermal problem, structure problem, fluid problem. You can solve them all at the same time with just a few keyword templates, which I will demonstrate in a second. Okay. All right. So with the overall workflow, right? So what I have here is a couple things to remember, right? The first thing is that the time step for structure, which is controlled by the control implicit auto, the time step of fluid, which is controlled by the ICFD control time step for thermal, which is controlled by the control thermal time step. These three things right here, they are the ones that really changes how your problem behave, and each of them have to fit with the nature of what you'll have to do for each of the specific physics problems, right? For example, your ICFD time, you have to be small enough to capture the transient effect, for example. Your thermal step time is for convergence. Your control time step for structure is also for convergence. So you have to make sure they are all individually satisfactory for each of the solver. Then you have to make sure they couple together correctly, right? You have to consider how they're going to couple together in terms of the DT. The DT is very, very different. Is that really adequate? Maybe you have to reduce the DT even further to allow you to account for a strongly coupled fluid structure interaction problem in which you have to set your structure DT to the same as your fluid DT. But for your fluid DT is going to be way smaller, which is what makes the FSI problem very expensive to solve. Okay? Alright, it's often a very good idea to test out each side, before you go to do a very complicated system coupling. One beautiful thing about Dyna is that, as I'll demonstrate in the example problem, is that you can set up individual physics very, very easily in Dyna to test them out, because you just have to suppress a few keywords. It just changes the behavior. And that's what's so beautiful about it, right? That you can actually manipulate what kind of physics problem you're solving directly in the input file by just suppressing a few portion of your code blocks. It is super, super awesome to generate. And of course, your control solution right here, look at the nature of what problem you're actually solving, okay? So you have to usually set it to 2 for a multi-physics problem. The ICFD boundary condition right here, right, are basically for your FSI, for your conjugate heat transfer interface definitions. These are usually need to be included to define the interface properly. All right, I'm gonna share my code template with you for a second. I'm still modifying these code templates, right? Because I'm still slowly working on these things to make it better over time. But what I have here is something that you may have already seen, right? It's for a basic CFD, FSI, CHD problem, right? You have these standard things you have to do. You have your CFD parts, CFD volume. You have your CFD mesh, which is your boundary layers and definitions, and so on and so forth. You have your initial condition, and you have your interface condition, and then you have your solver setup, and then you have your database, and you have your control cards, right? These are the things that's always going to be available. And of course, I have some turbulence card here that I can also choose to do. And down here, I have my thermal solver, right? Then I have my structural solver, right? So these are the individual pieces for every single CHD, FSI, CFD thermal problems that I can set up. These three-way system coupling that I can do. These cards is going to form the basis for all of it, right? So I just have to go through this keyword template, copy paste it to my preprocessor, and then suppress and delete the things I don't want and add the things I do want. A lot of this is about calling specific part ID and set IDs that I can essentially just establish, right? So you set up your CFD part first, you define your wall conditions, right? And then you set up your structure side, define your loads and your support. And on the thermal side, you define your initial temperature and whatnot, and define your thermal solver conditions. And then you define your interface, and then you tie it all together, right? And then you can define your structural solver setting, and you can define your thermal solver setting. All this right here, I have 500 lines of keyword, even though it looks like it's a lot. This right here, in my mind, formed the basis of the entire thought process for a complex three-way coupling problem, right? this type of fluid structure and thermal problem right here can all be handled with a single keyword template. And this keyword template can just be slightly modified for each nature of your problem to account for what you're trying to do. But the basic principle behind it is exactly the same every single time, which is why it works, right? I'm not trying to click button inside the software, right, to make it work. I'm basically setting up essentially a code block that will work every single time by properly adjusting the template, right? You know, it's like vibe coding almost like. It's almost like a vibe coding. You get the code from ChatGPT and you just run it. It won't work right away, but if you adjust it, it'll work to your purpose. Same thing here. I just created a template for myself instead of getting this from ChatGPT. I just created it myself, and it will work almost every single time with some adjustments. And that's essentially what's happening here. Okay. All right, that's the first video. I'm gonna make 4 more video for different examples, right? So the second video is gonna be about a very simple CHD problem in which I have water flowing through a pipe, and it's gonna heat the surrounding pipe materials. Second example is gonna be essentially a von Karman vortex, except in this case I'm gonna heat up the ball, have the water be very, very cool, and then I'm gonna have the water flowing through the ball. Then I'm gonna add some motion to the ball to look at how to couple 3 ways for fluid structure and thermal, right? This example is gonna be a little bit more interesting. So this example asks the question, right? If the solid is not always inside the fluid, what happens, right? So can I gradually move a solid into a fluid domain to heat it up or cool it down? Imagine this fluid domain is like an oven. How do I do that? I think the data transfer in the interface allows us to do this, right? So I'm gonna test it out to make sure I can actually do that correctly. And the last problem is gonna be essentially like a roller, in which I'm gonna heat up the roller just like the first problem, except in this case I'm gonna move the roller in a along the center rotational axis while the water is flowing across it, and then I'm gonna pull this piece away from the roller. I'm gonna define a tie break contact here so I can peel it off, and then I'm gonna sort of ask the question, you know, how long does it take to cool down or heat up this pink material? And then how does that affect the force that I'm applying, right? So this is essentially a 3-way structural thermal fluid couple problems. Still very simple, but in this case I have more going on the mechanical side to give us a little bit more challenge to test out my code blocks and test out my keyword templates, right? Also test out against the principle I've outlined here. But I believe I have captured everything I needed to do for this kind of problem. With the keyword template, right, I will be able to set up all of these problems with ease, which is the beauty of what I'm trying to demonstrate. Okay, I hope this is helpful. As a first video, it's not going to be very interesting because I have no demonstrations, but this is intended to be a 5-part video, and I hope this is going to be useful to you. All right, thank you very much.